Thank you very much. So I've got the enviable position of coming after Keith and before the end of the day, but I'm going to talk about near infrared astronomy. Some of you may be thinking, well, hang on, shouldn't we talk about optical astronomy first? And arguably, optical astronomy is simple. People always assume that near infrared astronomy is hard, and it's a little bit more tricky, but I have to show you that the things that you can learn from it, you can't get any other way, definitely make it worth the extra fiddly steps involved. So I'll start by telling you about what it is that makes the near infrared different. Now when I say near infrared, there's various definitions in terms of what larger wavelength range does that really cover, but pretty much I'll be talking about the region between 1 and 2.5 microns. So you often hear people talk about sort of the far optical up to 1 micron, and many optical CCDs do have some sensitivity even out to this regime. But when you get out to 2.5 microns, you need a different type of material, detector, to be sensitive to that. And there are some of these detectors that give you sensitivity right out to 5 microns as well. But given that really the access that many Australian astronomers have here in Australia and even in facilities elsewhere, generally only get out to about 2.5 microns, so that's sort of where I'll be focusing.
Sure. Can I ask you to actually go over to that position and do it from that way? So it's just, sorry.
Okay, so I'll cover specifically the different types of observing methods that we need in order to do infrared astronomy. I'll talk a little bit about the data reduction steps involved, but I won't show you any particular pipeline reduction. I'll do it very manually, just so that you get the steps as we go along. And then I'll finish up by telling you why would you even bother doing all this work with some examples from my own research that has benefited from this type of observing. So in infrared astronomy, the sky is your enemy. It's the thing that makes life particularly challenging. So the first thing to do, typically in optical astronomy, if you're looking at stellar sources, generally the sky background may be something on the order of about 1% the brightness of your source. Whereas when you move to the infrared, the sky background itself is typically hundreds of times brighter than the things you're interested in. So clearly that's a challenge. And just to give you an example, these are the sort of background sky brightnesses that you might get from a place like Siding Spring in dark sky. By comparison, the brightnesses in these near infrared bands several hundred times brighter. So that's a challenge. The next interesting thing though is that in fact the sky tends to dominate, the infrared sky dominates the emission at those wavelengths. And indeed, this curve here shows you the emissivity of a black body at about, let's say, 283 Kelvin. And this could be, in fact, much of the bulk atmosphere. But of course, also, don't forget your telescope is a warm black body with a temperature not dissimilar to this. So typically, everything you see in the infrared is emission coming from the sky or from the telescope itself. Note, however, that in terms of the impact of moonlight, obviously quite significant down here in the optical, but by the time you get down to the near infrared, it doesn't really matter whether you're in dark of moon, grey time, or bright of moon. You're still dominated by this the emissivity coming from the sky. And that's why, therefore, nearly all of infrared astronomy is done in bright time, because it doesn't really matter if the moon is up or down. Of course, you can do infrared astronomy in the dark periods. Good luck getting observing time then, because you're generally competing against the cosmologists. But there's nothing special that says you have to observe in bright time. It's just that typically that's when most of the infrared astronomy is done. Within the atmosphere itself, there are absorption features due to combinations of carbon dioxide and water vapor. And in fact, there's only the 1 to 2.5 micron region I've talked about. There are really only sort of 3 specific windows that we can even observe in, and not surprisingly, this is where the J, the H, and these K bands are defined to be to try and avoid these particularly deep absorption troughs at about 1.4 microns and between 1.85 and 1.9 microns as well. And the thing is, the amount of this absorption depends upon how much water vapor there is between you and the source. So obviously there are things like effects with elevation, the more air mass you're looking through, the deeper this absorption will be. But it also means that the higher up you can get, above ground level, the less water vapor, which typically is most prominent at lower altitudes. And so that's what makes sites like Mauna Kea in Hawaii particularly good for infrared astronomy, because the amount of this absorption is much reduced compared to a more temperate site like Siding Spring. Now, in addition to this absorption features that you see in the atmosphere, there is also this forest of emission lines. I'll show you a bit more detail here. This is taken from Mauna Kea. And these are airglow lines, vibrational transitions of OH molecules, which generally pretty much then dominate the background superimposed on the thermal component, dominate the background in the J and the H, and even partly into the K band as well. And so you've got these emission features on top of a already quite bright background, which pretty much fill the entire space. So if you're looking for a weak emission line in amongst this forest, you think it's going to be pretty hopeless. Albeit this is a fairly low resolution spectrum. I'll show you what happens at high resolution shortly. And as if that wasn't bad enough, you've got the fact that all of those emission features that I've just shown you are not constant in time, they're changing. Let me show you how. Let me show you what happens in a movie, courtesy of. Looks like I'm having Keith's problem. It was working earlier.
You won't have to exit to play it.
Well, I can't show you too. Never mind. But look, what you will see is that over the timescale of just a few minutes, the intensity of this emission changes with position and with time. And the reason why this happens is because the emission from these OH molecules is stimulated by gravity waves, not gravitational waves, gravity waves in the Earth's atmosphere, squeezing the atmosphere and stimulating the emission of these OH lines. So it's like looking at cirrus, except in this case it's not absorbing, it's actually emitting in front of you. And that structure changes spatially and with time. So yeah, it really is a bit of a nightmare to deal with. So arguably you have to be pretty determined to do infrared astronomy, but as I'll show you, it's worth persisting with. So the thing about to be successful as an infrared astronomer, you never stand still. Okay, I would like to say you can always spot an infrared astronomer in the crowd because they're the ones who are always fidgeting and moving around, never staying put. Whereas the optical people, we just sit there and lounge for hours at a time, no big problem. So the thing is, don't stare, jitter, or jitter, whatever you want to call it. You'll see it used interchangeably. But the idea is to keep moving around. Because given that these things are changing so quickly, you need to be able to monitor those changes and compensate for them afterwards. So the trick to that is to move your telescope relative to your source, only by small amounts, and I'll come back to that later, so that you're constantly able to sample what's going on in and around the object of interest. So by jittering, it helps you compensate for variations in quantum efficiency between pixels on your detector. It can help compensate for some of the pixel cosmetics that Kyla and Keith talked about. If an object lands right on a bad pixel at one position, once you move your detector on the sky, hopefully it'll land on some good pixels next time. And in the cases where you have gaps between detectors in your array, particularly now with modern mosaics of detectors, particularly in the near infrared, there are going to be gaps between the detectors because that's where the readout electronics has to go. But by, again, moving your detector around on the sky, you will get sampling at all locations. You'll be able to fill in those gaps afterwards. It also means that if you take these vivid images where you're constantly moving them on things, if you then take just a straight median stack of images, it's highly unlikely that at a given pixel on your detector will always have a star at that location at every single pixel. So by simply taking the median of those, the high values will be probably where you've got contamination by a star or a galaxy or something. The low values will be potentially with a bad pixel or whatever, but the middle value hopefully then is reflective of the sky brightness at that location. And so you can use a median made up of a stack of these vivid images that do help you then track these variations of sky level and structure while suppressing the actual stars and galaxies. And I'll show you an example of that later on. The other reason you'll keep moving around is, given how bright the sky is, your detector pixels actually fill up quite quickly just with sky photons. Forget about your objects, which is only a small contribution to that. So typically in the K-band, for instance, you wouldn't really expose for typically longer than about 15 seconds, depending on the site or also your pixel scale. But after 15 seconds, you've already used up much of the depth in those pixels. So you then need to read out your image, start again. And so if you're going to be constantly reading out your detector, you might as well take advantage of this and keep moving all the time. And even in the J-band, typically up to about a minute as long as you can go before you start to reach that same threshold. So let me give you an example of how we do this. So I'll give you a very simple example. We'll start with like a single jitter, possibly also known as a nod. So the idea is you take your first exposure at a particular position on the sky, which includes your object of interest. And when you read it out, this is a very raw image from the IRIS-2 camera on the AAT. But actually, the thing that you see, there's a few stars in the field, but actually mostly what you're seeing is, in a way, it's a bit like a flat field because you're filling all the pixels with light, albeit not of uniform intensity. This is just from the sky, which is, as you know, has some of that structure. You'll also see this sort of strange curls and things here. These are intrinsic to the fabrication of these detectors. You get these sort of what we call silicon swirls. It's just part of the fabrication process. But you'll see this pattern in every single image that comes out of IRIS 2, and you can compensate for it with these median sky flats I'll show in a minute. You can also see there are some dead pixels in the middle here. There's typically seems to be quite a few around the edges. So there is some information in there. There is some star images, but it's pretty hard to pick out just on its own. But let's then offset the telescope, let's say 1 arc minute to the east and 1 arc minute to the north, and take another image. Okay, same kind of thing. You still see that very similar structure, but now the stars land on different pixels compared to what they were before. If you take the difference of those two images, well, you get something that's it's not too shabby. You can actually start to see a lot more stars for a start, and your sky background is relatively flat. But of course, it's also filled with negative images of all the stars in your field. So, aesthetically, it's not very pleasing, and even scientifically, it would be very hard to do, so let's say, photometry, just using a simple image subtraction like that. But to first order, you can. It's amazing how much more detail you can see just by simply subtracting two shifted images. So let's take that to the next level, which is, let's say, maybe do it like a 5-point dither. We start centered on the field. We then move up and to the left. Okay, take another exposure there. We then go down and across. Okay, so now we've sort of done a 5-point star pattern on there. So we've now got 5 images that sample in different ways the field that we're interested in. But if we just take those 5 images, don't shift them in any way, but simply median combine that stack of 5, again, typically the 4th and 5th brightest pixels we'd assume are probably contaminated by stars, let's say. But the 1st and 2nd ranked images might have sky, but they could also be due to some other defects. But hopefully the middle value then is reflective of what the actual sky intensity was at that location. And in fact, that's what you end up with, just a median combination of those 5 images. The stars are gone. Okay, there's no stars, no galaxies. All you're seeing then is effectively the sensitivity of your detector modulo the brightness of the sky structure of those OH emission features during that particular period of time, which, given that let's say we do 1 minute at each of those locations, this is sort of averaged over 5 minutes. And hopefully that's quick enough that any changes in the sky are going to be slower than that, and so we can use this image as our sky reference. And if we then subtract this sky from one of our raw pointings, we get that, which actually isn't too bad by itself. You can now start to see the stars much more clearly, and now there are none of these negative residuals that we had before when we simply did pair subtraction. But it still needs a bit of work. There's clearly a few pixels that are not properly sampled yet, and there's quite a bit of rubbish around the edges. But if we do the same kind of thing for each of the 5 images that we had before, and then we use software which can detect the star, the point-like sources in here, and do a cross-correlation to work out the shift between them. We'll then align all of the 5 images to each other, and then combine them together as a mosaic. We get that. And now we're finally getting something. Now we can start to do astronomy on this. There's pretty good signal, nice smooth background, and so we can start to do astrometry, photometry, etc. And that's basically how we do it. And the key to it is never stand still, always keep moving. Okay, now that's a good strategy if you've got a field of relatively blank field, in my view, stars and stuff. What if you're interested in things like galaxies, which I am? But galaxy like this is an image, unfortunately, kind of too well, but this is AAO2016, which is what's called a luminous infrared galaxy. It's quite luminous infrared because there's a great burst of star formation happening, and that's because there are 2 galaxies in the process of merging. In this particular case, I'd like to be able to make an image of this galaxy here. This is the field of view of my camera, but as you can see, even from the optical, the galaxy itself fills most of our field of view. So if I do the standard trick of moving, let's say, some fraction, 10 to 20% of the field of the camera in each direction, pretty much every image that I take is going to be filled up with galaxy, not with sky. And so the techniques I've just described to you aren't going to work very well because it's contaminated by the extended emission. So to do the same kind of thing here to make an image, we can do our standard dither pattern on the source here, but to get the sky, we need to then go off and do a dither pattern similarly on adjacent blank sky where there is no contamination from the galaxy. Of course, what this means is that you have to spend half of your time looking at blank sky and not astronomically interesting sources. But that's a price you have to pay in order to make these techniques work. And when you do that, you can get images of this sort of quality. This is done using Gemini's laser guided star adaptive optic system. And this is looking into the core of this galaxy here. And this scale bar here, this is 1 arc second, right? So this is, let's say, average typical scene in the optical at sighting spring. In which case all of these bright nuclei here, plus these clumps here, would all be blurred together. You could not resolve them. But if you were looking for new point sources, which is what I'm doing, you're looking for supernovae occurring in the Starburst galaxy, you really need this very high spatial resolution that you can get with a combination of laser-guided star adaptive optics, which generally only works well if you're observing at the infrared wavelengths. And tomorrow's talk by Mike Goodwin about adaptive optics will explain how all of that works. Okay, let me move on and talk about how we do spectroscopy in the infrared. Really, in some ways it's simpler because we simply go back to that two-step nodding approach. This, if we say start off with a star first, and we put the star on a slit in one location, integrate for, let's say, 30 seconds, we get this spectrum shown here. These are these OH skylines that we see here. This band at the red end, this is where that thermal emission is really starting to come on in the K band at this end of the spectrum. So we get this one here. We then move the star by dragging using our guide probes. Usually I'll look at an adjacent star. We then move it to a different location on the slit, take another spectrum, and then, just as we did before, we simply do a difference of those two. And here we actually do it pretty good because over the course of a minute, those skylines haven't had a chance to change much in intensity. And so as a result, we get a pretty nice, clean subtraction with very little, few residuals. Of course, it helps that we have a very bright source to begin with. This would be let's say, an 8th magnitude star, so it's not surprising we get pretty good signal. And here in this case, if we could then extract the spectrum along here in ways not dissimilar to what Keith described, we could actually do the same thing up here, where of course what we would do is maybe cut this half of the image, separate it off. We would then multiply it by -1 to turn our negatives into positives, and then just co-add that flux to the extracted flux down here. And job pretty much done. However, what if you're, again, interested in something more exotic like a galaxy? First of all, it's more extended, so it may take up more rows on your detector, but the principles are the same. We would integrate for a few minutes here, and over that longer time scale, of course, we see the OH lines get much stronger. We then nod to a different position on the slit, do the same kind of thing. Now, let's suppose that that galaxy, though, maybe was much, much larger. Here again, we might need to offset to a completely black region of sky in order to get clean sampling of the object, because if the galaxy was too big and we simply subtracted the two, you'd be subtracting part of the galaxy from itself, and that would be very useful. The difference of those two, you can see now, first of all, is a bit weaker, and because we've had to integrate for longer at each position, it's going to be really hit and miss if we're able to achieve perfect subtraction of those OH skylines. And here we haven't really quite achieved it, although some of these residuals we can generally patch over in the data reduction afterwards. So it's not devastating. But more importantly, we are now able to make out much fainter features, emission lines, that were not present, that were almost impossible to make out amongst that forest of OH lines earlier on. Okay, so how do we go about reducing that data? Similar to the way that Keith described. Here again, we do the standard steps of wavelength calibration using an arc lamp. In this case, either krypton or argon are generally fairly good in the infrared. Although, to be honest, of course, don't forget, we actually have an arc lamp in the sky. It's called these OH lines, and most of these lines are pretty well catalogued. Unfortunately, there can be very slight shifts in their wavelengths depending on the condition of the atmosphere. So they're not ultra stable, but if you had, particularly in some regions where there aren't too many arc lines, sometimes your OH lines or OH residuals may be quite useful in that regard. You could use it as its own arc lamp. We've then gone, and for the galaxy, I've extracted and co-added those two nodes back to the object, and this is what you get out of it. And well, here we see what looks like a prominent emission line. There seems to be strong absorption down here, but in fact, this absorption, much of it is not intrinsic to the galaxy at all. This is caused by the atmosphere, and so we want to be able to get rid of this. And the way we do that is by taking those observations of that star that I showed you earlier, and ideally we want the observation of our star to be at a similar air mass to the way we observe the galaxy, because that way the amount of absorption, the depths of these absorption features should be pretty much identical, and they should cancel out. Indeed, you can see that here. We get very similar structure imposed partly by the atmosphere, but also by the response to the instrument, but it has these deep absorption features which are also seen in the galaxy. Now, there is at least one feature in this star, however, which is intrinsic to the star. If we don't correct for that, that will produce a spurious emission feature in the galaxy, which we don't want, because we're interested in real emission in the galaxy. And in fact, it's this line up here, which is bracket gamma absorption at 2.166 microns. The reason I know that is because this particular star that I've observed is an A0 star. And as many of you know, A0 stars, they have very deep, strong hydrogen absorption line. So you think, why would anyone use that as a reference? Because it's got these whopping strong lines in it. Yes, it does, but because they're so strong, they're very easy to see, and they're also quite easy then to remove digitally in software. You just basically do an etch-a-sketch and you patch over that, it's gone. Okay. Other people I know much prefer to use solar-type stars, where these types of features are much weaker. But then, of course, your spectrum is contaminated by lots of other lines, metallic lines and so forth, which if you would be almost impossible to remove and ultimately produce a whole forest of little emission features in your galaxy, let's say, which you don't really want. So, it's a bit of taste, depends a bit on what sort of science you're trying to do, but my preference generally is to go for A0 stars as your reference. So we've removed that feature, we then divide that into the galaxy spectrum, and now suddenly we can start to see what's going on here. There is, in fact, even amongst, and we've now compensated for much of that absorption, and out of that we now start to see this line, caption beta, coming out, which wasn't at all really prominent before. We now have bracket gamma intrinsic to the galaxy. We even have a bit of some helium as well. And out here, we can begin to see these absorption bands, which are due to carbon monoxide in the atmospheres of red giants. But it's still not quite the right shape, though, because we know that the spectral shape of this, this is not the natural continuum shape of the star. This has had structure imposed on by the spectrograph. But we know, because it's an A0 star, I know what shape its spectrum should be. It should be a 10,000 Kelvin black body. Okay? So I take the black body curve for a 10,000 Kelvin object. I then multiply that against this, and out of that I've now finally get a nice flat continuum object which has these emission features and also absorption. So that's how we get data or science out of a fairly ratty looking spectrum to begin with, but by compensating for all the different effects of the atmosphere and the instrument. So you might say, well, look, wouldn't it be nice if we could get rid of those OH lines? Well, two ways to do that. You can either go into space and do it with Hubble, or people have tried to do this from the ground for a number of years. This was one of the earliest attempts I'm aware of where people actually tried to physically remove the OH lines. What they would do is take light through a fibre into this cabinet here. This was a system that was built at Cambridge to suppress it, where they would then disperse the light at pretty high resolution. They would then bounce the spectrum off this reflective mask, which the locations where the OH lines are expected to be had been blacked out. And so only the gaps between them, where we didn't expect OH lines, would be silver, would have a reflective coating. The light was then put back into the spectrograph, undispersed, and then put in through another spectrograph at lower resolution to actually do science with it. Now, it was a good idea in theory, but in practice it was extremely difficult to get much light through it. It only had about a 1% useful throughput. And the other problem was that due to thermal effects, the spectrum would keep shifting relative to this mask. And so sometimes you get really good cancellation, and a few minutes later you get quite poor cancellation. But it was a brave attempt to basically knock out those OH lines and get rid of them from your data before you start to do science. Nowadays, I'm pleased to say we have much cleverer ways of doing it. Remember, I talked about the light comes off the telescope, comes through a fibre. Wouldn't it be, if you're going to put your light through a fibre, why not get the fibre to knock out those skylines? And the way you can do that using what's called fibre Bragg gratings. This is a system that's been pioneered here at the AAO through a couple of instruments, originally Gnosis. We're now building a new thing called Praxis. And the way it works is we take, in the optical fibre, we use a laser to modulate the refractive index through the centre of the fibre and effectively produce an artificial diffraction grating. And as a result, the light comes through at particular wavelengths, is reflected back up the fibre, up into the sky where it will be lost, but the information, the astronomical information, which is everything other than that, passes through the fibre. Again, sounds simple in theory, getting it to work in practice has been a bit more of a challenge, but I think you'll expect to see major breakthroughs in this area into the future, such that these OH lines will be almost a thing of the past that we won't have to worry so much about anymore. So you might think, well, look, if it's that difficult, why would we bother observing the near infrared? Well, several reasons. First of all, the extinction due to dust in the K-band is about 1/10 of what you see in the optical. And of course, extinction, like being a Manchus, this is actually a much, much greater factor. So if you want to see deep into dusty regions, such as the dusty regions where stars are being born, which typically are dust enshrouded, or the dusty torus around the black hole, you have to go to infrared wavelengths. Optical is very, very difficult. If you're doing redshift surveys or trying to measure star formation rates, metallicity and so forth, the emission lines that you're interested in the optical, once you get to about redshifts about 1 to 2, you have to follow those into the infrared. So you're going to have to observe at those wavelengths anyway. There are lots of really useful diagnostic lines that we can use, which are only seen in the infrared, but they can tell us about the physics of what's going on. Brown dwarfs, particularly the very cool ones, the T dwarfs and even the Y dwarfs now, about the only flux we ever see comes out in these near infrared bands. So that's where you've got to get your spectra if you're going to put a type on them. And as we'll come back to tomorrow, adaptive optics, which enables you to approach the diffraction limit with these 8 meter class telescopes. For instance, you get down to about 50 milliarc seconds at 2 microns. So again, the infrared is the place to be. You can't really get to the diffraction limit in the optical at the moment. Okay, I don't really have much time to go into the science that we can do with it, unfortunately, but I'll just give you a couple of highlights. So, for example, here's in the centre of M100. There are lots of star-forming regions at the core with gas being fed from the bar. And by comparing the strengths of these emission features to the absorption features with our models for Starburst, we can put constraints on not just the age of these objects, but also the characteristics of their burst, whether they're short or long extended features. The other thing we can do is sort of science I've been doing recently with Gemini and now more recently with Kent, and that is looking for missing supernovae or supernovae that would otherwise be missed in these luminous infrared galaxies like ARC-299. Unfortunately, this doesn't come out terribly well, but let me just say one of these images comes from the Hubble Space Telescope, and the other one is down from the ground using laser guide star adaptive optics. And I challenge you to work out which is which, but basically this is the one from Nick Moss on the HST back in 2004, this particular LERG. And this is the same object imaged 4 years later from the ground with Gemini. And the thing that we were able to see fairly quickly, without even doing a subtraction, is that there is a new source here that wasn't present in 2004. This is a supernova that we found in our 2008 data. Not only that, we even realised that there was an object in 2004 which is no longer present. So that was not the supernova back in 2004 that nobody recognised because there was nothing to compare it with. But the great thing is, therefore, we don't have to rely only on Hubble to get this kind of spatial resolution. We can do this kind of stuff from the ground, even in the near infrared, where life is challenging, but not insurmountable. And there are pretty well-established techniques and data reduction software that's available to overcome all of this. And there's several reasons why you would want to use these techniques to observe the near infrared. And it's also worth keeping in mind, of course, that many of the current generation 8 meter class telescopes, and pretty much every one of the new extremely large telescopes, GMT, TMT, and European ELT, they're optimised to work at the near infrared wavelengths by the use of adaptive optics. So don't be afraid of the near infrared. It's a really cool, exciting place. You just have to never stand still when you're observing the near infrared. So I'll finish up with a few references. There's some really good resources at the Gemini Observatory webpage you won't find anywhere else. And also I can recommend this book by Ian Glass if you want more of the fundamentals. So thank you very much. Questions for Stuart?
Yeah. So I was wondering, like, I know in infrared astronomy, like, when you're even exposing a field, you take, like, you read the CCD in read pairs. Can you explain a little bit about that?
Yeah, so one thing that surprises people about infrared detectors is that they have no shutter. Okay, you would think, well, how can you observe if you don't have a shutter? Surely you want to keep the thing nice and dark and then open the shutter, expose and close the shutter. The thing is, as I say, in addition to the sky filling up all your pixels, there's also thermal noise, even when you cool these things down to typically 70, 80 Kelvin. If you had a shutter, you'd still get charge and signal building up on your detector fairly quickly. So what you want to do really is, and unfortunately Kyla didn't have time to get onto this afternoon, but infrared detectors are not CCDs. They're sort of hybrid CCDs where you have a readout, what's called a multiplexer underneath it. And on top of that you have your the substrate which is actually sensitive to near infrared radiation. It could be a combination of mercury, cadmium, telluride, or it could be indium antimonide. But the great thing about these particular detectors though is you can read them what's called non-destructively. So unlike the CCDs, which once you read them out, you've destroyed the information that was there. You then have to start taking another exposure. Whereas with these infrared detectors, you can sample over time to see how the signal is building up. And so we make use of this technique. Generally at the start of the exposure, or what you call your exposure, you do a reset on the array. And then after your exposure time, let's say 10 seconds, so you reset the array, you do an immediate read, even though you don't expect to see anything significant. But you will, as I've mentioned, there will always be some signal because these things are continuously generating response, photons, electrons in the substrate. You then wait till your 10 seconds have elapsed or whatever, and then you do another read. And you then take the difference of those two, which is the signal that has accumulated from the sky in that time. And that way you don't really need a shutter at all, because all you're doing is comparing from the start of your exposure to what's built up at the end of your exposure. And in fact, if you're doing things like spectroscopy, where typically the backgrounds and the sky signals and everything is much reduced, what you would do then, because when you do those before and end reads, and you take the difference, that gives you a measure, but it's actually more accurate rather than measuring the difference between those two. If you could measure the rate at which the signal is building up and then fit that rate, potentially get a lower noise result. And that's what we do in spectroscopy. So during spectroscopy, we might integrate for, let's say, at least maybe 2 minutes at least, sometimes 5 minutes. But in that time, we take one read at the beginning, we take one after, let's say, 20 seconds, and then another one at 40 seconds, 60 seconds, 80 seconds, 100 seconds, and we sample those, and we then fit them in software as we're reading out the detector. And what we then get out as a result is not sort of that difference between the end and the beginning, but simply fitting the rate of growth. And generally that gives us a much lower noise per pixel than if we were to simply take the difference between the two. It is a slower process, which is why we don't use that method if we do an imaging, but it is a much more way to effectively beat down your read noise if you're doing spectroscopy, where typically you're much closer to being read noise limited rather than background limited that you would be in imaging.
Yes.
I didn't have a question until you answered that question.
So
in this case, where you're defining an exposure time,
yeah.
In this case, you're not really opening and closing a shutter, but rather you're defining an initial and final time that you're sampling of the readout.
Yeah. So things would you let's say it's in the K-band, as I said, you probably wouldn't want to go more than about 10 to 15 seconds before you'd almost filled all of those wells. So you would then do 10 second and 15 second integrations. But if you then had to move the telescope every 15 seconds, you would spend less than maybe only 20% of your total time would be spent integrating. The rest of it would be overheads moving the telescope.
And is there a constant sampling frequency? So you're just giving it like the initial and final time, but then it's kind of getting the growth, the curve at specific intervals, or?
Yeah, generally we can do that. There's also other methods. For instance, some of the because we can do these reads non-destructively, some systems, some observatories go to, they'll actually read the detector multiple times at the beginning and multiple times at the end, and then take those difference in order to get a better measure of that rate of growth. But just come back to, as I say, rather than do sort of 15 seconds move, 15 seconds move, what we tend to do is, let's say 15 seconds, and then store that difference as a result, but don't write it to disk as a file, because that's going to take time. You then do another 15-second read, okay? Take that result and put it in memory, do another 15-second integration, and you do this, let's say, 4 times, and you then co-add those 4 individual exposures and write that to the disk as one file at that position, and then move the telescope. Okay, because otherwise the data rates, as Keith alluded to earlier, would be simply horrendous. And that's generally the way that we've observed with IRIS-2, for instance, and that gives you the gigabyte per hour or so sort of total data quantity. And again, that's by building up, integrating, averaging, beating down the noise characteristics. But nevertheless, it's trying to strike that balance between the overheads involved with having to move your telescope, shifting your guide probes, and all that kind of stuff. And inevitably, there's always penalties to be paid on all of these things. But these are some of the tricks you need to play in order to be successful at observing the infrared wavelengths that optical astronomers generally don't have to worry about. Although, to be fair, a lot of optical techniques now astronomy is starting to borrow from these techniques, like obviously nodding along the slit, dithering at different positions for much the same reason. It's just that you can spend much longer staring at one patch of sky before you have to move. Whereas in the infrared, as I say, keep moving. That's the key.
Yep.
Yes.
I've got another question about the detector. Is that once you finish the target and you move on to the next target, how do you prevent ghosting or flush the detector, so to speak?
Yeah, well, so this is, and we do this persistence that Kyla mentioned is a particular problem with some of these infrared detectors. Well, the first key is always trying to avoid really bright stars. Now, of course, as we get to a bigger, wider field infrared detectors, that's becoming harder and harder to do, because almost inevitably there's going to be objects in your field that you can't really do much about. But again, that dithering technique can be your friend, and that, okay, on one hand, it will move that bright source and put it on many different parts of the detector, but then hopefully you'll still be able to recover the information on the fainter sources from regions which are not affected by that persistence. Generally, in the infrared, in fact, because even when you're not integrating, we are continuously flushing, reading out the detector, and in so doing, slowly flushing out that persistence problem. But sometimes, if you really do cook it at the beginning of the night, it can affect you for several hours afterwards. So you do generally, even though there's no shutter built into the system, we do encourage our observers with RS2 to move in the slit wheel. We do have like a blank position, which keeps the duo relatively dark and just minimises the risk that maybe during a slew to a new target or something, you might inadvertently slew across Jupiter or the Moon or something, which would be pretty bad.
If you know you're going to have persistence for a bright object, you can predict it, then you just subtract it out at the expected intensity, and then you've got shot noise issues, but the total intensity from the object is removed.
You can also avoid putting your science object to that part of the detector in your dither pattern, which when you hit the auto dither, you probably want to check the positions that your science object's going to end up in if it's coincident with that object.
One more question. Will the James Webb Telescope have anything of interest for you in terms of instrumentation near infrared?
Yeah, well, in fact, so the James Webb Space Telescope, of course, is always portrayed as the successor to Hubble, which is actually not true. It's more of a successor to the Spitzer Space Telescope, because James Webb is really fully optimised, not even for the near infrared, but for the longer wavelengths, the mid-infrared, sort of 3 out to 20 microns or so. But it will have cameras that operate all the way down to 600 nanometers, so the red part of the spectrum. And of course, 6.5 metre telescope in space, clearly it's revolutionised things. But on the other hand, you have to recognise that it's not the most responsive telescope, being out at L1 and difficulties involved in slewing the telescope. So it won't be particularly good as a rapid response system that even typically Hubble itself can do at the moment. So we're still going to be in many ways as reliant, if not more so, on ground-based infrared astronomy in the era of the James Webb Space Telescope than perhaps we currently are now.